So, yeah, this meeting is being live streamed. This one here.
So it says.
Good. Right. So, all being well, you should all be able to see my screen. So, thanks very much for coming along to tonight's Not IoT. We've got a nice user group here. So, we've got a code of conduct. There's a lot of words here, but they boil down to pretty much that bottom right one. Just be kind and considerate, and everything will be tickety-boo. It's all good. But there's a bit.ly there. You can go check that out and read the full code of conduct. But if anybody's got any problems, then by all means, just send me a direct message and I'll endeavor to put right what once went wrong, like Quantum Leap said. So with that in mind, moving on just a little bit, if it'll let me. There we are. Our sponsors for tonight are JetBrains, Calyx, and my company PJG Creations. JetBrains are sponsoring us a license to any single one of their products. Now, JetBrains make developer tools for developers, so that's everything from IntelliJ and Rider and ReSharper, WebStorm, PHPStorm, loads of tools like that. So to be in with a chance of that, just send a tweet during the event for the hashtag NotsIoT, and then at some later point, I'll draw out a winner for that. Calyx are also sponsoring us a piece of IoT tech. I've not been very good at drawing this actually, so I think I've got a bit of a backlog. But if you do the same, tweet on the hashtag NotsIoT, then unfortunately this is just a UK only competition. Mainly because of cost of postage to other parts of the world is just prohibitive. It ends up being more than the cost of the IoT device often. So if you're in the UK, by all means, look out for that. There's a good chance you could win a piece of IoT tech. I'm an MVP, and in fact, there's a few of us on this call that are MVPs. In fact, there's what, 5 of us? Because Shorty, you're an MVP, aren't you? Are you an MVP? Oh, okay. Well, we need to rectify that problem anyway.
I've tried twice and been turned down.
Okay, well, we'll fix that.
Brian nominated me once as well.
Right, we'll have to fix that. But Sander, Jose, and myself, we're all Microsoft MVPs. What that means is that for doing community work like we're doing today, so the 2 speakers, for instance, or myself running this user group, you do enough of that sort of activity and you get recognized by Microsoft. And that opens doors into Microsoft itself, where we get access to preview information coming down the line, direct access to product groups and things like that, as well as some perks and benefits like Azure credits and Office and Windows and things like that. But really, it just gives you the benefit of getting closer to Microsoft. If, you know, being in that Microsoft space is something that gratifies you anyway, then it can be quite a useful thing to do. So if you've got any questions about that, then ask the MVPs I've mentioned earlier, including myself, and we'll be happy to divulge the information that you need. Tonight we've got Peter Shaw, or Shorty, I think you just far prefer to be called Shorty, and Jose Simões talking about nanoFramework and hacking Lego Mindstorms. So we'll get on with that shortly. Coming up next, actually, this is the last .NET Not IoT of the year. We don't traditionally do one in December. We have done, but it tends to be, you know, people want to do their Christmas shopping. So we'll be back in January, I believe. Actually, we've got Sander coming back in January. So quite looking forward to that. Sander's talks are always good as well. But I'm actually speaking in person at .NET Knots at the end of the month. So I'll be talking about how we can take Azure Cognitive Search and Azure OpenAI and combine them together to be able to gain insights out of your own documents, your own data, which there's always a million different ways of doing it. But I think the way I've done it is quite a good way. So do either come along in person to that or tune in on Zoom. Either option will be available to you there. And with that, that's enough of me chattering on. I'm going to stop sharing and pass you over to our 2 fantastic speakers. While they're getting their sharing set up, if you just keep yourselves on mute during the talks, and then if you've got any questions at all, just stick them in the chat. And then while they're talking, I'll interrupt them with those questions at a moment that's convenient for them. It just keeps it flowing a little bit more. I think you said this is probably roughly an hour and a half long. So somewhere in the middle, we'll take a break so that folks can go to the toilet and top their coffee up. But other than that, I'll step back. I'll probably turn my camera off because I think I'm going to have dinner in a minute. But I will still be here. So enjoy.
Right. I'll kick off. So, as Pete said, this is .NET nanoFramework and Lego hacking. Sparse slides from me, unfortunately, time commitments. Roughly, this is what we're going to see tonight. So, Jose is going to give you an introduction to .NET nanoFramework. I'll take you through a getting started demo. So that'll be live. We'll fire up Visual Studio and do the good old fashioned blinking LED one. Then we'll probably go for a break sometime after that. And then after that, we'll actually dive into how you can hack your Lego NXT systems and make them do interesting things using .NET Nano. Me, I'm no stranger to those of you who've been on .NET Not IoT before. I think this is my third, or is it my fourth appearance? I can't remember. I'm just an idiot that loves technology, a northern idiot that loves technology, and I basically get paid to pull things apart, figure out why they don't work, why they work, how to make them better, that kind of thing. Jose, I'll stop my share there and I'll let Jose introduce himself.
Thank you, Shadi. Let me share my screen then. All righty. So I'm José Simões. I'm CEO and founder of Echo Solutions, a company I work from 2003. I'm also the founder of .NET nanoFramework, which along with a couple of friends back in 2016. But we'll see that in a moment. We've started this spinning off .NET microframework. Like Pete already mentioned, I'm an MVP on developer technologies and IoT, and this is me. I thank you, Pete and Shoti, for the invitation on being here. It's always a pleasure, and I hope you guys like what we have to share with you tonight. All right, about a little bit about nanoFramework. This is part of the .NET ecosystem. Okay, our goal is to write C# code for resource-constrained microcontrollers, and this means that we can run this on very small microcontrollers. And small, it's even smaller than the usual Raspberry Pi that you probably maybe have used in the past. We can do ESP32, SMT32, and a bunch of other platforms, and we'll dive into that in a moment. Being .NET, this allows you to use all the .NET ecosystem that you probably are familiar with, from the NuGet packages to working on Visual Studio. You have the same coding and debugging experience, just like if you were doing a desktop application or an Azure project or anything like that. So we are basically part of the .NET ecosystem, and we are also part of the .NET Foundation. And a bit of history of nanoFramework. This all started back in August 2016 when I tried to make microframework more community oriented. Not being possible, decided to spin off the project and basically revamped the whole thing. Kept the good parts that were perfectly working, got rid of the ones that were not so good. All the build system was completely redesigned from scratch, so it could be easy to use, easy to bring in new platforms, easy to bring new microcontrollers, and a bunch of stuff related with being flexible and running on more platforms than it was. And this keeps going on and on and on until we reach. I can stop here maybe in the middle. It took us roughly 2 years until we thought that we were production ready to get our very first release. And then we joined the .NET Foundation on September 2020. We keep adding new tools and new libraries. We have used an interesting mark on February 2021. We come up with a unit test framework. And then keep moving. Our latest big milestone was back in June this year when we brought to the family a new platform, which was the giant gecko from Silicon Labs. Okay, this is our last platform that we added to the ecosystem. Just a few numbers so you can get a rough idea on how many people are using this, and we now have 242 NuGet packages, which is a lot. We are almost at the 16 million NuGet downloads, which is rather impressive if you ask me. I'm surprised with that, which is a statement on how popular the project is. And know that this particular statistics of NuGet are gathered from NuGet. It's not something that we do. So we are using caching on our pipelines that we use. So there are other mechanisms behind this to prevent us from artificially boosting the numbers, so we don't have any machine keeping doing downloads to increase these numbers. Over 20K on Visual Studio Extension downloads, and this is it. We live on GitHub, like pretty much every other open source these days, and a bunch of code lines, more than 90 repositories, lots of stars. We have a growing number of contributors. We have a very friendly and competent community around nanoFramework, from the Discord server to people that are usual contributors. We've seen a lot of traction there, which is pretty cool. So what is nanoFramework? This is basically a subset of the .NET CLR, to be small and efficient, and of course to be able to run on constrained embedded devices. Otherwise, it wouldn't be possible to do this with the common run times. So we have a subset of the of the base class libraries, because we cannot have them all, of course, otherwise this wouldn't be Nano. And we try to carefully pick and select the APIs that are more interesting or relevant to be used or likely to be used on embedded systems development. For example, you can find pretty much the same stuff that you find on the full .NET, just that, for example, we don't have so many overloaded APIs. We try to pick only the more interesting ones, and try to be careful about that, because the flash and RAM space is at premium on microcontrollers. But we have the same stuff that you find on the full .NET. You have threading, you have math, you have collections, you have JSON, you have the system net, you have the file IO, and you have, of course, all the other good stuff more related with embedded systems like I2C, SPI, serial, Wi-Fi, and so on. So from natively it supports multi-threading, so it means that you can start your threads, and this and the CLR, the execution engine, will take care of executing them on a round robin fashion, just like the full .NET does. And this way you can split your workload across different threads, and you don't have to do anything special, because that's baked in on the execution engine. Okay, our API is aligned with the full .NET for the majority of the libraries, and it's for the more embedded world ones, like the buzzes that I've mentioned, I2C, SPI, and so forth, with .NET Core IoT. Okay, so if you are using the Core IoT on a Raspberry Pi, you can run pretty much the same code with very little changes in a microcontroller running nanoFramework. That's one of the reasons for this API alignment. Okay. This is capable of running on any 32-bit core, and we'll see more details on that in a moment. So, and this is basically it's two RTOS threads running on the microcontroller. We sit on top of an RTOS because we need that to provide and to take advantage of what the RTOS brings in, from semaphores to queues to scheduling and all that stuff. We need that to make the things run smoothly. That's the reason why, and we support several of them. And also interesting to know what .NET nanoFramework is not. So this is not an RTOS, okay? Like I was describing, it runs on top of one, but it's not an RTOS per se. Okay, it's an execution engine that executes a string of IL instructions. It doesn't have a JIT, and we don't have also any ahead of time compilation or anything like that. It's executing IL. And obviously, it's not able to load and execute standard .NET assemblies. One of the reasons is that probably even the MS Corelli wouldn't even fit on the flash. So that's the size is one of the constraints there. That's why we have our own CLR and our shrunk version of the APIs and all that, like I was describing. Okay, a quick overview on the architecture. On the higher layer, we have the user application and libraries, which is what developers, you people probably, write your code, your Visual Studio projects. This is C#. Okay, and all this is referencing the system libraries, which are all distributed as NuGet packages. Okay, so this makes it very easy to maintain, to bring in only the what you absolutely need for your project, so you don't waste flash nor RAM, because this is something that it's constrained on a microcontroller, as you know, and all that sits on top of the nano CLR. This is where the native code comes in, and this is all written in C, C++, and assembly. So this is the I won't go into too much details here, but all the stuff from the CLR to the PAL to the HAL, down to the hardware, it's there. And as we move up in these layers, we get more common stuff. As we get down to the HAL, it's this is all different between platforms, which it's one of the good things about nanoFramework is this platform compatibility. Unless you are using on your application something that is platform specific, you can run it on any supported microcontroller. This kind of brings in the promise of .NET build once, run everywhere. So if you have an ESP32, you can do your code there. And if you are not using anything platform specific, you can just grab the exact same project and deploy it to an STM32, and it will work out of the box. Okay, which is something very cool and interesting. Supported platforms, which is the devices nanoFramework runs, and that we have ports to. Basically, any 32-bit core, from the ARM Cortex to RISC-V, any of the fancy extensive, which are the ones from the early days ESP32s, and some of the newer series. They have some RISC-V in there, and also worth mentioning on what this resource constraint meaning is that the minimum viable microcontroller to run on a framework requires this staggering amount of 128 Ks of flash and 64 Ks of RAM. From there on, you are good to go. Of course, you won't be able to do anything too fancy with this amount of flash and RAM, but it will give you a very good start on what you can do with nanoFramework. So you'll agree with me that's very low requirements to be able to run C# on a microcontroller. A bunch of RTOS that we have ports to, from Chibius, FreeRTOS, TI RTOS, Azure RTOS, you name it. The build system is designed in a way that we can bring in new RTOSs and new platforms relatively easy. So it's designed for that. So if you need to use a different RTOS because you prefer, because you have better support, because your company uses it, it's possible to do, and the build system is prepared to work on that.
The questions in the chat if you're interested.
Okay.
Some guy called Sander, I don't know who that is. Is MQTT version 3 and version 5 supported?
Yes, we have support for all those. The MQTT library, it's very well maintained because that's one of the building blocks for the Azure and for the Azure IoT library and also the AWS. So this is well maintained, and we have, yes, compatibility for version 3 and 5.
Excellent. I'm sure there's a couple of MQTT applications that Sander is particularly interested in there, given some of the blogging that he's been doing recently. And Paul has asked what C# language versions will work with it.
Yeah, this one is tricky to answer. We support most of the language versions up to 9.10, but there are some features on the old versions that we don't support. So it's you can go and edit your CS proj, NF proj file in this case. And set there which language version you want to use. But know that there is a listing of the limitations that the nanoFramework has. So basically, if you are trying something fancy, it probably won't work. But most of the features on all versions, they are supported. Okay. And this is easy to spot because usually it ends up right on the build. If you hit F5 and boom, so it's a clear indication that that feature is not supported. Okay, hope this is
on the. Sorry, I thought you were finished, Joe. Go on.
No, I was saying that I hope this is a good enough answer to your question, Paul.
I was just going to say on the subject of the MQTT question. The MQTT support and the Azure IoT libraries are very, very well supported. I actually, on one of my clients, they were writing their firmware in C for a new startup that they've built, and I converted them to C# and nanoFramework. And when they took one look at the fact that the nanoFramework code was about 300 and odd lines less of code than the C++ version that they were using, they were absolutely over the moon with it. And there's no way that they'll ever go back to using the device's SDK in C++ again. It just works fluidly, absolutely fluidly. It's really well implemented.
And also doesn't make your eyes fall out of your head when you look at it.
No, it doesn't. Absolutely.
Good, but yeah, and adding to that, Shorty, actually the Azure SDK library, it's the only one that we have that we completely deviate on purpose from the standard API for a very good reason. The official API on the Azure sucks, and it makes it very complicated to use. And so, being on embedded and being on Nano, we took the opportunity to do an incredible simplification on all the APIs. So we just it has what maybe a dozen calls. You have it. You have everything work from. You just call connect and you throw in your parameters.
Yeah.
And it just works. And you have all the good stuff that you are expecting and that you have on the desktop library. This will be from the messaging, cloud to device, device to cloud, the DPS support, authentication from certificates with keys, whatever, direct messages. You can set up your callbacks. All that stuff is there and implemented on a very straightforward way.
It is. It's all very easy. It's just if you're used to using .NET events in a normal .NET application, you just hook up an event and it's done for you. It did throw me a bit of a curveball at first when I first started using it, because if you remember the discussion that you and I had on Discord, Jos, and I got told off by your co-author for doing things the wrong way. Because I didn't realize just how much they'd simplified things and how much they deviated from the API. And I was trying to program my C# version using the same patterns that the C++ version would have.
Yeah.
And then I got my wrist slapped, and now I do it properly.
All right. Okay. So it's a very good library and very well maintained. So back to our reference target. Just a quick overview on the platforms that nanoFramework has ports to. Pretty much all the STM32 series, F0, F4, F7, L4, H7 is in the works. We have support for them all. On the SP world, also pretty much everything. I think this is on PR right now, the move to the ADF5, because right now we are using the ADF4, and this is something that the people using ESP will be more familiar with. This is the SDK that it's beneath the nanoFramework and acts as the PAL and the HAL layer, okay? We support pretty much all the series, and the ones that we are not supporting yet will be supported on the coming weeks, because that's already on PR and being reviewed right now, the move to the IDF5, which will bring the rest of the series that were there. And they are ready to flash firmware images for pretty much any module, any SP32 module that you find out there. From the rover kits with displays, without displays, the dev kits, the feathers, the M5 stacks. We have firmware, dedicated firmware for all the models, the feather ones from the unexpected maker too are there. Moving on to another platform, the TI, we have a firmware image for the CC3220 and also for the 1324, which is that's the tiny device there. It's not the bigger one. And this one is the 1352. It's a very interesting device which brings in, it's a dual core, the Cortex dual core. And brings one of the cores runs the application, meaning nanoFramework and whatever is there, and the other one is responsible for the radio stacks. Okay, so it's pretty efficient. This basically can be a multi-protocol radio protocol device. You can have it talking any protocol that you like that works on the ISM band or the 2.4. Okay. Another one is the NXP. We have a port for this board and for this series. This is the only one for NXP. And a bunch of other ones. You have here the Scilab Sky and Gecko that was the latest one being added to the ecosystem. This Orc Pulse 3, it's a customer board that from a US customer and a long time supporter of nanoFramework. They have a telemetry system deployed with a huge number of the devices. They are doing mostly telemetry, and that's their thing. Now we have work in progress for several others, new series and other platforms like the analog devices Max 78000, the Pico, which is something that is every other day someone asks if there is a port for the Raspberry Pico. It's also in the works. Actually, someone mentioned on Discord the other week that there was a Japanese developer that published an article on one local embedded systems magazine there, and that made it a port for the Pico. We have one of the community members who is also in Japan has reached out to that guy, and they are working now to make this publicly available. So we probably will have support for the Pico sooner than later because of this. Most of the work, if not all, it's already done. So this is good news. nanoFramework is your platform for building almost anything, like the slide says here. You can use Visual Studio, you can use the command line, and you can develop web, cloud, mobile, IoT, AI, because you have all the power that it's brought to you by nanoFramework ecosystem. And from all the 200 and something NuGet libraries that we have available on NuGet, you can get libraries for pretty much anything, from the standard libraries to interact with the devices, and also a huge collection of IoT bindings, which kind of in sync with the .NET Core IoT, and we have libraries and bindings for a huge number of sensors, motors, displays, you name it. Just go to the IoT bindings repo on our GitHub, and you will find there literally hundreds of them. Worth noting that nanoFramework can be used not only as a prototyping platform, or if you are coming up with a proof of concept or something like that, but this is production ready, and it's being used by several commercial companies in commercial products throughout the world. And for that, we have professional tools that help you have a barcode, and you can do exactly the same stuff that you do on your nanoFramework projects, like you use on the big full .NET on the desktop. Starting with a unit test framework, you can have unit tests. They can be run on a virtual device, or they can be run right on the hardware. Okay, so it really depends on what you're doing. And this has the same look and interface that you have on the Test Explorer on Visual Studio that you are used to. You just have the same interface. You can run them on a command line, everything like that. We also have a logging library, which sometimes can be useful when you want to leave an application as standalone, running stuff and logging whatever it's going on there. The log can be output to a file, to an SD card, to a UART, to a socket, so you can grab it on some point in the network. All that is available there. We also have a very nice benchmark library, which is based on the popular benchmark.net, on which you set up you decorate the pretty much like the unit tests. You decorate methods with attributes, and it can run the benchmark there. You can compare with all the versions. You can compare between methods, and all the good stuff that you found on benchmark.net. We probably have that implemented and available. There is also a bunch of build scripts available on our GitHub to take care of the CI pipelines, and this being on Azure DevOps or on GitHub Actions. All that is there because we use both on our builds, and this is something that you can grab and adapt. Most of them are even publicly published on the Actions library on GitHub, or on the Azure DevOps marketplace, so you can reuse them on your own pipelines. It's there, and this is something that happens throughout the nanoFramework project. Everything is 200% open source. From the tools, from the CLIs, the Visual Studio extension, the libraries, everything is open source. So you can pick and what we are doing, what we are using, and we are using our own tools. So it's proven and tested daily. Okay, so this is it.
Awesome.
Right, so I'm sure you're all eager to want to know how to put all this into use now. So what I'm going to do is I'm going to switch over to my screen, and we're going to do the obligatory getting started blinky LED thing. Now at this point, I will have to stop my camera in there because I'm going to share my screen and open the camera on there using the camera application so that you can see my ESP32 while I run Visual Studio. So we'll just get that up and running first. There we go. Now we need to do some gymnastics here. Just bear with me. So we just focus in on this little gadget here. You can see that this is just a standard, absolutely bog standard ESP32 W room. This particular one, I think, came in a box of 5 from Easy Delivery off Amazon for around about 15 UK pounds. So literally you can pick these things up probably for about £1 a board. Now, the first thing you need to make sure is that your device shows up with the proper COM port drivers. I'm not going to go through that process, but if I just plug it in there, you'll see, there we go, we actually have the COM port for it. So once your COM port shows up and it's fine and it's there, you know you're going to be able to use it. Now, mine's blinking already because I was just test programming it while Jos was doing his part just to make sure that everything was working fine. But when you initially plug one of these in, you won't have the .NET Nano framework on it. So the first thing you need to do once you've got it plugged in is you need to have the nanoF tool. And that's a .NET tool, just like many others. I cannot remember the syntax for that, but it's .NET a .NET
install.
Sorry, say that again, Josh.
.NET tool install.
That's the one. .NET tool install.
-G for global.
-G for global.
And nanoFF.
nanoFF. Now,
this is the short thing for nanoFramework flasher.
Yeah. I'm not going to actually install it because I've got it installed, but that .NET tool there, once that is installed, that will give you access to the nanoF command line. And just type nanoF on its own and it'll list some help, and it's got the usual sort of dash help and all that kind of stuff on. With your board plugged in, you need to then update the platform you're choosing. Now, in my case, mine is on serial port COM8. If you recall, there it is there. And I'm using an ESP32. There are other platforms. I'm sure there is a list command to list all the platforms that are available. If not, I'm sure Jos will be able to tell you off the top of his head what they are. But in my case, this is what I need for the ESP32 board. So running that, it will take a minute or two to do it. Depending on the speed of the CPU, it can take a little while to read the details from the chip. Also, don't worry about reprogramming it more than once either. I mean, I've already flashed the firmware image onto this before we started the session tonight, but reflashing it again is absolutely not a problem. Just as I say, sometimes it takes a little while. So while that's doing that, I'm going to launch a new version of Visual Studio. Well, there we go. So no sooner do I move away from the command line than it actually does what I want it to do. So it'll actually erase. Another thing worth noting as well, sorry, is when there is an update to the base libraries in nanoFramework, you will need to do this same update command on your board to update the firmware. I can't remember off the top of my head the error message that you get, but if you go to deploy an application from Visual Studio with a newer version of nanoFramework, you will get errors about not being able to deploy the various versions of the libraries that it's trying to put onto your device. And if you get those version errors, it is generally because you need to do this update to make sure that the base image on your device is the same version as well. Now, as you can see from the camera, that has now stopped flashing. And that's because it's got a brand new firmware image on it, but no user code. So the next thing you need, we'll just continue without code for a minute so that I can go in and show you the extensions, and Zoom helpfully obscures the menu bar. But if you go into your manage extensions and just go to the Visual Studio Marketplace and search for Nano, you'll get the nanoFramework extension. Now again, as with the other bits and pieces, I've already installed this for mine. So we'll just close that. And I'll restart Visual Studio. I shouldn't have gone no code, should I? But never mind. Once you have the extension installed, the rest is absolute child's play. So I'm just going to go create a new project, and in my search we'll go Nano, and we'll pick a blank Nano application and Blinker 2 and create. And the usual Visual Studio chugging will take place. Just give that a moment. And there we go. So this is our default application. When you first open something up in when you first create a Nano application in Visual Studio, you'll simply just get a debug, and then it'll go into an infinite loop. Now, one thing you might not see on your screen when you first create your app is this device explorer here. Now, you will need that. So if you don't see it, view other windows, and you'll find your device explorer in there. Once your device explorer is present, before you press F5 or before you try to run your code in any way, make sure that you click on and select the device that you want. If your device does not show up in there, then you can press a button here, rescan Nano devices to rescan. Now, I do apologize about missing icons. There is a bug in the system. I believe it's a Visual Studio bug. But hovering over them, you get the tooltips, so you'll be able to tell which buttons which. Do we know if there's a fix coming for this anytime soon, Jos, or is it something that you've been wrestling with for a long time?
We've been fighting with this for a long time, and this has to do with the resource loading for the image files, and this is something that it's being tricky. And this came up with one of the version a year ago on Visual Studio, and we are in touch with the Visual Studio developer team, but so far we haven't been lucky on having this fixed.
So if you don't get your icons, don't worry too much. All you simply need to do is hover and the tooltips will tell you. If we rescan just quickly, you'll see in the output there, you can actually see the scanning. I believe there's one here as well to turn on extra details. I can't remember which one it is.
It's the one to the left to the rescan devices. No, actually, it's the one that is it's highlighted because it's
okay, because
yeah,
I've got the details turned on. But the point being with the device explorer is you need to have your device present, showing up in here, and you need to have it clicked on before you press F5. If you don't, you will get deployment errors. And if you're not too up to date, if you're just starting with this, the deployment errors can throw you off. I know they did me the first time I ever used this. Once we're up and running, you need various packages from NuGet. Everything, as Jose mentioned in his slides, is modular. It is all 100% modular. It's broken down into the smallest elements possibly. Just about every application will want the nanoFramework core library in it. That goes without saying. And in most cases, if you've used the wizard to create your application, that will already be there for you. For us to do our Blinky, we need access to the GPIO. So in here, we're just going to do the usual NuGet thing. And we're going to go nanoFramework. And even without putting anything else in there, you can see the amount of packages that we have available. We have I2C stuff, we have GPIO. We've even got a lot of the stuff from the main C# libraries. We've got IO ports there. And another one worth looking for as well are these IoT.device libraries, because many of the devices that you will commonly use, such as LCD displays, data acquisition devices, you will more than likely find that there is existing a converted driver from the standard IoT network already, or the nanoFramework community have contributed a driver of some sort for it. If you look on the nanoFramework GitHub page, I believe there is a whole repository that's just dedicated to the drivers, right? Yep.
Yes.
Yes, I thought there was. And, you know, I mean, if you've got a weird gadget that you're trying to plug in, look on the devices page first. You probably will save yourself a lot of headaches. Now, in our case, we just want the GPIO because all we're going to do is blink the built-in LED. So we'll just install that as normal. As you can see right here, right now, it's standard C#. I've not done anything that is in any way particular to working with microcontrollers. Check out those links, definitely, especially if this is your first rodeo with nanoFramework. All the samples are there, the documentation, and if you do go into Discord, just be mindful to get things right, otherwise you might get your wrist slapped. Little in-house joke there. So once you've got your packages installed, it's then time to start writing your code. So we're just going to using system.device.gpio. And you can see the IntelliSense works properly as well. So everything that the guys have done with nanoFramework is all fully IntelliSense. Get rid of the boilerplate code. To access the GPIO pins, you need a GPIO controller. So we'll put GPIO controller, GPIO cont there as a variable. And then we will set that GPIO. Yes, of course, it has to be static, doesn't it? Right, let's see if I get it right this time. Yes, yeah. Let's see if we get it right. It's okay. I do this all the time when I'm doing WinForm stuff as well. I forget that everything's static, and then I wonder why I can't access my variables. Right, we'll try that again. So then we need to initialize our GPIO controller. Again, IntelliSense, there we go, new GPIO controller. Now, once you've got your GPIO controller, you are going to want to create a pin to work with, and that can be found in the GPIO pin class. We'll call this LED, and we're going to use the GPIO controller that we just created a moment ago to open the pin. Now, on this board that I have, the built-in LED is on pin number 2. There are constants for some of the pins, GPIO pin numbers and pin modes and things like that. In fact, you can see some of them in the IntelliSense pop-up there. I'm not going to mess around with that. I'm just basically going to use the number 2 because I know it off the top of my head. But if you're using a lot of different pins, it's worth putting constants at the top of your application, because then if you decide to change your pin mapping, it's easy to just change the constant rather than have to go through and change anything else within your application. We want to use this as an output pin, so we're just going to set it as pin mode output, and we'll initially turn our LED off by writing a pin value of low to it. And that's the essence of writing to a pin. Now I'm going to cheat a little bit here, and I'm just going to paste in the loop from the Blink example from the nanoFramework samples, rather than type all that out, because I'm sure you've had enough of me ham-fisted hammering the keyboard at the moment. You can debug this and in exactly the same way as you would normally. You can see I've got my device selected. It's on building and deploying now. And there you go, you'll see it's hit my breakpoint. I can F10, single step through everything. And then when I want to, I can just press F5. And where's my camera gone? You can see, there we go, we have nice little blue LED blinking away, courtesy of C# running on a tiny little microcontroller.
Very nice.
Everything...
Quick question in the chat from Paul. Can you use async patterns, or is it all blocking? It's a good question.
That's a good question. I think that's one for Jost, that one.
We don't have support for async await. That will come along with when we have generics. But you can do pretty much the same, of course, using a different pattern with the threads and the semaphores and the weights and all that, because that's available from the threading library.
Very cool. And also, Cliff is acting as a co-pilot, which is actually against his way of working now, being as an actual full-on captain. Lines 24 to 29 are redundant, look. So
I beg to differ. That's because the last slip is a bit larger than the 3 befores, and that's why you see that effect of the ping ping boom
Ah, you see, look, see, I like it. Copilot's wrong. Love it.
Excellent. And just about anything that you want to do with the .NET Nano framework is this simple. I don't have an Azure IoT example at hand, but as I mentioned earlier when the question was asked, I took an app that a client of mine had running, and we reduced it easily by about 300 lines. I think their end application ended up being somewhere round about the 90 line mark.
If you want a really good example, Cliff Aegis, who's on this call, has made a nice IoT Hub nanoFramework blog post, haven't you, Cliff? So if you want to go see that, then I'm sure Cliff can drop the link in the chat for you.
Sure we can.
Yeah.
But that is really how simple it is to get started. If you stop that there, by the way, this is something that caught me out. If you stop that there, it actually holds the device in reset. So if you look back at my camera, wrong one. If you look back at my camera, you will see I've actually stopped it right mid-blink. So when you stop your app from running, especially if you've had it under control of the debugger, you essentially hold the board in reset. But if you unplug it and plug it back in again, it will then just continue running the application that you last deployed to it straight from afresh. Or if I press the boot button there, which I'm not going to, or if we use I think there's a reset, there we go, reboot target device, there's reset options and things under here as well. I was going to mention sort of the network configuration and stuff like that, but I think that's maybe a little bit advanced for what we're going to use. But if you're using the TCP/IP interface, particularly with something like an ESP32 that has the Wi-Fi on, you can pre-allocate the IP address and things like that. Stuff that you would normally use the ESP32 Bluetooth configuration app to change using Bluetooth Low Energy. So you can pre-program network interfaces and Wi-Fi profiles in without actually having to put them in your code. And they will be embedded into your application by the Nano framework when it builds them. At least I believe that's correct anyway, isn't it, Joss?
Yes, it is. All that is stored in non-volatile memory in the device, and you can store there the Wi-Fi profiles. If your device, for example, is roaming and connects to 2 or 3 different hotspots, you can have all those profiles there with the setting on the auto connect, meaning that when it drops one, it will start scanning for the whatever is available, and if it finds one that matches one of the profiles he has stored, it will connect there and get online again.
But you can upload your certificates.
Yeah, I was just going to say, yes. Finally, as a final note, if you're doing Azure IoT stuff, the hub certificates that Microsoft required you to use to connect to Microsoft IoT Hub are already baked into the framework and are put in there for you automatically when you build your application. So if you include the IoT libraries provided by the Nano Framework team, your certificates will be there and ready to rock and roll. And at that point, that's, I think, where we decided we were going to call a break.
Yeah, I think you've got another sort of probably a bit less, but similar amount of talk to do the other side. So if we take 5 minutes now, it should give people long enough to go fill up their glasses with whatever they fill it up with and go and turn themselves around in the toilet. and we'll carry on about 5.2, somewhere around there. So that was really, really interesting information. I love that. We love nanoFramework at Lots IoT and in the MVP community generally. So I know Cliff, who's on the call here, he talks about .NET on small devices like this, and is often talking about nanoFramework off at places like NDC. I'm normally on a Raspberry Pi actually, and let Cliff do the nanoFramework stuff. But I think I've got long enough between now and NDC that I need to get my build a 3D print another robot arm and take that out with me in an ESP32 and nanoFramework and hook that up at the same time.
Excellent
So
choice.
more than one robot. You're giving that exact talk the other side of Christmas at NDC London, aren't you, Cliff?
I am, yes. Yeah. So yeah, nanoFramework and the Wilderness Labs board. So I talk about both. Sorry, Jose, I know you'd firm your all nanoFramework, but I just talk about both, and yeah, and just talk about why you choose one over the other, that sort of thing. The good thing about nanoFramework that I love about it is the boards are super cheap, and you can get them from anywhere, including Amazon. Same day delivery I've had even from Amazon, whereas Wilderness Labs is you buy it one supplier, it's not a cheap board, and you have to wait weeks for it to arrive from the US.
Yeah.
So
it's a great board though.
It's a great board. Just depends what you're doing. That's all. You still can't do things like sleep and stuff like that with the Wilderness Labs board. So if you're running off a battery, good luck. So whereas ESP32, it just all works. So
yeah, I absolutely love the ESP32. When I first started digging into this, I got so many people telling me STM32, use the blue pill. They're great. They're the best boards. And honestly, I actually find them very, very underpowered. Compared to the ESP32. I'm really not that impressed with them at all. And bricking them is just stupidly easy. I've yet to brick an ESP32, but I've got a box full of blue pills that just are dead.
I got a box that's similar as well. I keep meaning to one day get around to seeing if I can get them back from the death by reloading sort of a different ROM on them or something like that. But yeah, they just seem to die on me really easy.
Yeah.
You have a hammer around?
I got a hammer, yeah. I got plenty of hammers. Yeah.
Lie them all flat on a work surface and lacquer the top, and have an awesome looking worktop.
No, I've got a great idea. How about an IoT world record? Just as Evel Knievel used to jump over double deckers, why don't we have a .NET nano-controlled, radio-controlled car and see how many dead STM32s we can make it jump over?
You'd need a plane, not a car.
You've got one of them, Cliff. In bits.
In bits, yeah.
The IKEA version.
Yeah.
Right, back in a sec. I'm just going to fill my water up.
The other thing that I'm really impressed with as well, the other device I absolutely love is the Raspberry Pi Pico.
Yeah.
Oh man, that is just crazy.
I just want nanoFramework to work on it properly. I know there's a community version out there, but last I looked, unless it's been done now, Jose, last I looked, it was still a kind of in progress.
It's updated. I did mention that before you join us. There was a guy in Japan that made a port for it and published an article on a local magazine. And one of the Discord members, who is also on Japan, has reached out to that developer, and it's working with him. So there will be soon a PR adding this to the official distribution, which is pretty cool, because much of the work is already done and it's working. So
awesome.
Good news there.
Yeah. Because they're just about to, well, say just about. I mean, they've dropped enough hints that there's going to be a Pico 2, isn't there? So hopefully it won't be too much different. And then nanoFramework will work on that out of the box.
Yeah.
Yeah. Cool.
Yeah. The first one is always harder.
Yes. Yes.
Every time.
We still need the Wi-Fi drivers for the MX chip, though. You understand? That's otherwise my cupboard full of them down here.
Yeah, I got a box full. I think all of us that went to MVP Summit have got a box full of them. Yeah.
Yeah. No more.
Sander took the most, I think. Yeah, there they all are. Yep, that's
it. Samuel took the most.
Oh no, Samuel did, didn't he? He took a whole box back to South Africa, didn't he?
Yeah.
He did.
Samuel won.
I have a pile of them in my desk to remember every single day that I have to finish the port.
Maybe what we should do, we should wrap one up and just post it to Jose, like one a week. Just keep posting them until he gets upset. A bit like, like sort of in Hogwarts, they kept posting the owls with the letters until the Dursleys give in. Until I've been watching Harry Potter on the movies with the kids recently.
Yeah.
But yeah, maybe we should do that. Just keep posting one until he sort of gives in and goes and does it.
Yeah.
Speaking of event giveaways, Peter, do you remember that Tinner Mouse thing that we all got given at DDD Sunderland?
I'm not sure I got one of those, Tinanimous, but the purple.
Tinnimus.
Yeah.
Yeah. Well, believe it or not, the network's actually still running.
Is it?
Yeah. I found my login and password the other day. He's made some changes. You've got to use his own format of JSON now. You can't just connect and consume regular MQTT topics. But yeah, it's all actually still up and running. He's still got it going. I think he's only got something like 10 subscribers worldwide, and that's the 10 of us that got the free lifetime subscriptions for presenting at the conference. But I was remarkably surprised, and it's quite fast as well, considering.
Yep. Right, should we get going with the second half?
We shall indeed. Right. So I'm just going to share to my slides now. So here's where the good stuff starts. Right, can you all see that?
We can.
Good stuff. Right. So now that we know how to use .NET Nano, and we can make our devices do some interesting stuff using the language and the frameworks that we love, now it's time to actually have some fun with it. So why might we want to hack a Lego NXT system? Well, many of you may not realize, but Lego has now officially discontinued all of the Mindstorms product line. That includes the more modern versions like the EV3 and the Spike Prime. And Lego NXT systems now are going for absolutely silly amounts of money on the collector's markets on eBay. Last time I looked, just for a brick on its own, for an NXT, people were asking round about £300 for them. So if you've got a brick lying around, you can either flog it and buy yourself a box full of ESP32s, or you can start crack it open and adding your own bits and pieces to it. The Lego NXT system itself originally was quite a closed source system. Lego did, you can still find them scattered around in various places, did produce a set of software development kits and a hardware development kit for it. But the documentation wasn't exactly top-notch documentation. It generally consisted of a few protocol diagrams, a few circuit diagrams. So you very often had to work out a lot of the byte sequences for yourself, why they worked the way they did, how they worked the way they did. However, once you get into the system, anything that the NXT brick can do, it's absolutely possible to make your devices now do using the .NET Nano framework. In reality, you can use any framework you want, because most of what you do is just toggling GPIO pins and sending digital comms. But with Nano framework, that does make it much easier. Not just the NXT. The NXT I chose to do my experiments with was because I had it to hand. But once I actually cracked open my older RCX one, and I looked at some stuff for the EV3 and the Spike Prime, the NXT, EV3 and Spike Prime all use the same 6-wire cables. The older RCX use a very simple 2-wire cable, but the actual underlying methods used to drive the sensors and the PWM for the motors, which you'll see later, are all done in exactly the same way. You only really need to break your connecting cables. Now, the problem with that is that many of the cables that people use, I've lost it. Many of the cables that you get with your NXT kits are specific to the kits. You only have the right number of cables for the kits and the models that are in the books. So you may not want to cut the cables open. If you go trawling around on eBay and you look for these guys that are doing house clearances, you find that many of them will sell random bags of Lego bits. And it's worth looking out to find bags of cables. I did have my bag to hand. Oh, there it is. I was actually very lucky in that I picked this up. I think it cost me about £5. And it gave me lots of spare cables, which in turn allowed me to make the adapter cables that I needed for this project and for this session. You can also use a regular RJ12 telephone plug with a little bit of modification. And the company Dexter Industries did used to do breakout boards, but they no longer make them or supply them. So, what modifications do we need to do to the cables? Well, the modifications are actually very simple. Okay, I don't actually have one that's not plugged in, so I'll show you a close-up later. But the wire consists of 6 cores, and the 6 cores are divided into 3 primary groups. The black and the white cable are used for your PWM for your motor control. And you will make one of those active at a time, depending on which direction that you want to drive the motor. It's a regular PWM signal, so altering the duty cycle on the PWM will alter the speed of the motor as well. Your red and your green pair are generally your sensor power, and to make things absolutely crystal clear, Lego decided that your +5 volt would be the green cable and that your ground would be the red. So thanks for that. Your digital pair, your yellow and your blue, usually are your SCL and your SDA line, and they are connected directly to the system I2C bus within the NXT brick. If you are going to do some I2C bus implementations, you must terminate your buses, and they have to be 43K resistors. Now, I know normally in an I2C system, terminating the bus is something that you can experiment with a little bit, and you can also vary the values on the resistors. Because of the way the Lego NXT brick and system is designed, 43K resistors are a must. Dexter Industries found this out the hard way when they made their breakout boards, and they made their breakout boards actually with the 43K resistors wired into them. If you follow this circuit diagram that's on screen right now and take your 4.7 volts from the green line and terminate your resistors to that for the SCL and the SDA, you won't go wrong with it. The I2C device specification on these systems is not like your regular I2C device. There isn't a singular device number that identifies each of the different sensors. Instead, what Lego have chosen to do is they have one I2C number that basically means Lego sensor. I can't remember off the top of my head what that device number is, but every Lego sensor shows up with that device number. The first byte after the device number in the usual I2C scheme of things is the sub-device number, and it's the sub-device number that tells you what type of sensor you're dealing with when you're dealing with I2C ones. The non-I2C ones, touch sensors, sound sensors, they don't follow this protocol, so therefore you don't have to try and interpret the data for those. Mindsensors.com do sell ready-made cables, but they can be quite pricey. $9 for the shorter ones is not too bad, but if you start getting things like 50 centimeters and above, and particularly the longer ones, I found that plus the prices for the postage and packing from the USA to the UK is quite high. So if you are going to buy from mindsensors.com, what I would recommend you do is you order everything in one go rather than as separate packages. If you do decide to do your own cables yourself, Mindsensors will sell you a bag of plugs, the RJ12 plugs, already set up to work with the NXT sockets, but you will not have a crimp tool for them. And a standard RJ45 network tool won't fit them and will not work at all. In fact, if you try using an RJ45 crimp tool, you'll most likely smash the plug in half. I know this through experience. If you want to actually read back the rotary encoders on the Lego motors, which are built into only the NXT and EV3 motors, you need to use the I2C lines as a differential pair, which are 90 degrees out from each other, with a rotary decoder, such as, I forget the name, the PIC 18F4550, I think, has one built in. And when the yellow leads, the yellow leads, your motor's been moved forward manually. When the blue leads, the motor's been moved backwards manually. If you are not powering the motor, then you can use the white and black leads, I believe, for analog inputs. But if you are powering the motor, then you cannot do I2C or other forms of digital communication at the same time. The main thing to remember with all of these cable setups is that many of the wires are dual purpose. So depending on what port you plug it in on your NXT will depend on exactly what signal's on there. There is some standardization. If you are running an analog sensor, for example, then you should get your analog on the white and the black. So if you build your own sensor to plug into the NXT, one of the inputs rather than one of the motor drive ports, you should be able to feed analog voltages on either of those lines and use one of them as a ground reference. I've not actually tried that yet. It's on my list of experiments to work with. If you have a sharp enough knife and a very steady hand, then it is possible to take a regular RJ12 telephone adapter. These are for those who are not used to them, these are the little plastic plugs that you used to get on many of the broadband routers. You'd have the BT plug on one end and the little plastic one on the other end that plugs into the back of the router. That's the size plug we're talking about. I've tried doing it this way, and bloody fingers later and lots of swearing, I actually gave up. It is not at all easy, especially if you have quite hard plastic on the plugs. It is doable, but as I say, Mind Sensors will sell you the plugs if you want them. As far as I know, Mind Sensors are actually the only place that sells the plugs already made to fit a Mindstorms NXT brick. And a regular RJ12 crimp tool for the commercially available ones is absolutely no good for crimping the things on. So if you do make your own modified plugs, you are probably going to have to use a screwdriver to push the individual pins in so that they bite onto the cable and actually make an electrical connection with them. If you want to modify an RJ12 crimp to make your own plugs and cables, this is the site you need to be looking at: philohome.com/nxtplug, nxtplug.htm. Not only does he explain in detail how to soften the plastic up and cut the clip off and put your own clip on, but also how to take a commercial RJ12 crimp tool and switch it so that it actually bites on the opposite side and actually fits the Lego plug. If you want to make some money, then there's probably a market here in the UK for somebody making these cables for people like me who want to continue to butcher their NXT systems and not do things the normal way. Saying that, these are the modifications that I made for mine. So as you can see from the images there, I basically just cut a cable in half. I separated them out into 3 sets of 2 pairs, as described before: motor control, power, and digital I/O. And then I just put 3 2-pin DuPont connectors onto them. You can use 1-pin DuPont connectors, 6-pin, 2 rows of 3, anything you want. I just did it that way because it makes it much easier to plug them into my breadboard, and I can separate them out and keep them far enough away from each other to prevent stray capacitance if need be. If you've got the older RCX system, that's even easier. You just need 1 single 2-pin DuPont connector, cut your cable in half, put a couple of DuPont connectors on, and Bob's your uncle. The major difference with the RCX is there are only 2 wires active at a time. So if you're using an I2C sensor, then you've only got I2C across the 2 wires. If you're using the motors, you've only got PWM across the wires, and so on and so forth. If you want to connect up your Lego sensors to your ESP32s or your Arduinos or whichever device you're working with, connecting the touch sensors is as simple as it gets. As you can see from the circuit diagram here, all you need to do is take the black and the red, tie them together, and then basically sync a voltage via a 2.2K resistor to that grounded connection. How you do that switching is entirely up to you. You could have a transistor that's controlled by a microcontroller. It could be a relay, BJT, anything like that. As long as it is a simple on-off state. That on-off state will be interpreted via the touch sensor part on the NXT brick itself. The not so simple sensors are anything that is not the touch sensor. For example, the circuit diagram that you're looking at there is the one for the light sensor. And you can see that it uses 5 of the 6 cables in an altogether completely different manner to everything that we've seen so far. Now, I'm not saying that it's not possible to read these sensors yourself using your microcontroller, but it is certainly a challenge because particularly with things like the light sensor and the sound sensor, Lego do not release the details of the signals that are on the wire. I found out what I found out about reading these things through a lot of perseverance and hooking things up to oscilloscopes and logic analyzers and spending many hours reading the signals to see what actually appeared and where. With a bit of work, you can read these signals. You can get the proximity to the light, the strength of the light, whether it's over a white or a black. But it's not something that you're going to do in half a day. The I2C sensors, you can, if they are just a simple case of powering them, power them off the red and the green pair, and then hook them up onto the I2C bus. As I mentioned earlier, however, the I2C sensors that Lego uses are encoded in a different way that the NXT brick understands. Now, that's not saying that you can't read the I2C data from a Lego sensor into an Arduino or into an ESP32 using Nano, and then strip off that byte and just treat it as a normal I2C device. That's probably your easiest route to using them. But if you're going to create an I2C sensor that you're going to plug into your NXT brick, then you will need the hardware documentation and you will need to understand the byte order and the sub-device encoding for it. I do have a copy of the hardware development kit, and I do have a copy of the software development kit, and I will be making a GitHub repository available once we've done this session, and I'll probably put the bits of sample code in there as well that you'll see coming up. I'll make the zip files with the SDK and the hardware development kit available for download, which will contain the circuit diagrams and what public documentation I've been able to get that explains all of this. The slides will also be available, and I believe Pete possibly already has a copy available for download via this session. I'm sure he can clarify that later on.
Yeah, no, I've not uploaded them anywhere yet, but
Okay.
We'll be able to do that via Sessionize or something, and not Sessionize. What is it? SlideShare, and get them folks.
Excellent. And then once I get the GitHub repository up and running, I will give you a link to advertise to the group as well, so that they can go and find all the other bits and pieces. And at this part, I think I'm going to hand back over to Jos, because he and the rest of the nanoFramework team have been busy putting together some I2C code that allows you to create I2C slave devices using nanoFramework. Whether or not this will be as per the Lego spec or not, I don't know, but it shouldn't be too difficult to modify if that's the case. So I will stop my share there and take it away, Jos.
But just before that, did we get to Chris's question just there? Sorry, does nanoFramework support ice slave mode?
Sorry, I didn't see that. So what was that again, Peter?
Does nanoFramework support I2C slave mode?
And that's exactly the question that Mr. Simões is about to answer.
And yes, the answer is yes. It does. Especially for this meetup, this library was coded, and the idea, as Shoti was explaining, was to do crazy stuff with the bricks. But we'll get there. Anyway, the library is there now, and we have the master one, just like for the SPI, for a long time, actually from the very beginning, I think. And now we have the slave one. Currently, only the SP2 platform is supported, but support for the other platforms will be available, because most of the microcontrollers and the vendor SDKs do support both ways, the master and the slave. Okay. So what I'm going to show you next is how this library was coded, and this kind of can get you an overview on how this is done for the base class libraries. And this is particularly interesting because it has both the managed part and the native part, meaning that the manage is the one that runs on C#, of course, and it's common to all platforms. And then you have the native part, which is platform specific, because the SP32 handles I2C differently than the STM32 and so on. Okay. This is a typical Visual Studio solution with a class library project, which is what a base class library is. This one ends up being pretty simple, and there is nothing fancy here. You can see some properties here and some fields to hold the device address and device ID. But let's get to the constructor here.
Jose,
do
you want to zoom in just a little bit? It is a little bit small.
Sure. Looking better now?
Oh yeah. Well, can you make the text bigger? If you could just make the text bigger rather than zooming in like that, that'd be better. Yeah, there we are. Perfect. That's perfect.
Like this?
Yeah.
All right.
Yeah. Excellent.
All right.
Chris followed up, by the way, with what about SPI slave?
Yes, that's not available, but can be done exactly the same way, because most of just like I2C, most of the microcontrollers and the vendors SDK have support for that. Okay, so here the thing is, when we are instantiating an I2C slave device, we have to pass the bus ID and the device address. Here the bus ID, it's because most microcontrollers can support more than one instance of an I2C bus. Okay, on the SP32, on the base series, I think there are 3. There are the series that have 2 and others have 1. So this is the reason why, and that's why you have to pass here as a parameter on which bus ID the device will show up. Okay, and then of course the device address. As you know, each I2C device responds to its own address or to the general call, and that's why we have to have this one here. What this constructor is pretty simple stuff. It just stores on the backing properties the parameters that you are passing, creates a lock object, because this can be accessed by multiple threads, and we don't want to mess up things, blah blah blah. And create a buffer here to help on the transactions that we'll see right now. I'm just going to go through a couple of methods here so you can have an idea on how this works. This one here, for example, is when you want to read a byte, read byte on the slave device. Here, what happened is when you are calling the device, it will read byte. It will the result starting by the end. It will return true or false, depending if a byte was read or not successfully. You can pass an optional timeout, and it will an out parameter with the value for the byte. Okay. Here, the interesting thing, you can see that this is wrapped on a lock because of the very simple reason that being nanoFramework multi-threading CLR, you can have multiple threads accessing this slave device, and you don't want that to happen in order to not mess up things. So when one thread is calling this read byte, you don't want the next thread to mess up with that. So that's the reason for the lock here. Here the interesting part, it's this call to native transmit. Okay, we'll see in a moment what this is, and this is basically wrapping both the reads and the writes operations or transactions, if you will, that happens on the R2C device. Okay, in order to reuse code. We'll let's go here with the write. We've seen the byte, so let's see with the one with the buffer. We have this span byte, which is our poor man's span of byte generic version, which acts pretty much the same way as the generic version, but it's implementing without generics. There is an automatic casting from byte array. So if you just call this with write and pass a byte array, it will work just the same. It will take it. And here you can see this one is simply calling the native transmit thing there. Less interesting stuff, implementation for the disposable pattern, blah, blah, blah. And here, the thing that connects this to the native part. This can be done with any library that relies on native code. To make that happen, we have to decorate this with this attribute of the method implementation, and we signal that's an internal call. This exists also on the full.NET, but on nanoFramework, we are using this to pass the information to the compiler that this will rely on a native implementation. The other thing is the extern here, okay? So with these two, method implementation, internal call, and extern, we are declaring to the compiler that, hey, this when you call this will happen on native, okay? And this is basically it. When I build a solution and it builds, of course. Let me grab here so you can see what happens on during the compilation. Here, when this is built, I'm going to delete the bin and the object files, and I'll go back to Visual Studio and I rebuild this, and it will do it, blah blah blah. And you can see there is this folder here which is called the stubs, which is generated when we are compiling something that has native support. And what this does, it spits a couple of files, which are the stubs that will be filled with C and C++ code to make things happen. Okay, here this you can maybe you can recognize here the names here: native init, native dispose, native transmit. If I go back to Visual Studio, this is native init, native dispose, native transmit, okay? And all this, if I take it as they are, because these are stubs, they will throw a not implemented exception on any of them, okay? Here the pattern. The next thing, and this is what makes when the type resolution is happening and the microcontroller is booting and the CLR is booting, this is the declaration for this assembly, the system device I2C slave, okay? This is, I won't go into much detail here, but you can recognize here the functions with the arguments here. And this is the declaration that will make the ID or the signature, if you will, of this library, okay? There is the name, there is a CRC32 which is generated from the method names and the parameters there. This allows us to find out if you change something on the assembler. For example, you added there a new method or a couple of new methods, and if you try to run that against a firmware that was not aware of those methods, this bad things will happen. And so this is a very simple way of finding this. It runs a CRC with the method names and the parameters, and if anything changes, it will generate a different CRC32, and this way we'll find out when we are deploying that the firmware doesn't have support or doesn't have the correct version for this library, okay? And here a header file with the declaration for the field that you find on that class, and here again another way of the functions that will be implemented there, okay? One last file here, it's the CMake file for this assembly, which is already built, and when you want to add this library to the build system, you basically have to grab these 4 files in this case and drop them on the interpreter and enable the build with this library with the library name, okay? And again, I won't go into much detail here. I'll go now to where this is. Okay, this is where the stuff really happens. Now I'm Visual Studio Code again, but I'm on the NF interpreter repo, okay, which is where the firmware is built. Here, you will recognize here the same 3 functions that were that we were looking at the stubs a moment ago, and here is what really happens in terms of the code. This is somewhat less interesting to the C# developers, but this what this is doing, it's doing the initialization for the ESP32 I2C hardware block, like the work bus is going this to be set up. What are the GPIOs where this is going to be exposed, and what's the clock that's being used, blah blah blah, and it does a driver install, and you can see a bunch of stuff here that you can understand what's trying to do. Here I'll jump into the native transmitter, and the native transmitter, what we'll do is that it grabs the parameters that we are passing from C#, and let me switch to Visual Studio here. If you see here on the native transmit, what are we sending as parameters to this native method? It's the buffer for the read operation. It's the other buffer for the write, and here the timeout. Okay, I'm going back to Visual Studio Code now. And this is what we have here. Here. This is the return. And I have here encoded the type names. Okay. And this will be I won't go here again on details because this is somewhat complex. You can recognize here, I'm going to grab this, this will be a pointer on memory, and I'm going to, I know this is a span byte and it works a certain way, has a certain fields, and at the end, I'll just grab the data that is passed on that is on those buffers, and I'll be sending that through I2C, or I'll be reading from I2C, depending on the transaction that I'm doing. Okay, so this is part of the, this will be using that CMake file there, which is specific for this this assembly. We'll make the device I2C slave assembly and the implementation for the platform become part of the firmware. To enable this, the only thing that I have to do, and if you are familiar with this, this is the CMake preset, which is part of the CMake build system. What I have to do, it was not here because it's general for all the devices here. I just have to pass this configuration option here. I put here on the API, blah, 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 on, and the build system takes care of including this assembly on the build. When the build is done, I'll have a firmware which I can flash to my ESP32 device, and it will have support for the I2C slave. When I go back to Visual Studio, and I deploy an application that is referencing this NuGet, the system device I2C slave, it will have support for this library, and it will do its thing when we are calling this the various methods here, like the read, write, span byte, just read byte, write byte, blah blah blah, and all this stuff. So hope I didn't get this too complicated. This is how you come up with a base class library for nanoFramework. I can see there is a question. Oh, that's
fine.
Pretty cool.
So
no questions.
So essentially, what this means is that was just an example for an I2C slave device, but it basically means that you're not limited to the firmware that you download. You're not limited to just what the nanoF tool will program into your device. You can build your own extra parts to the framework to do anything you want without actually needing to do anything with the framework. Excuse me a second. Sorry, for those who were unaware, I tested positive for COVID this morning, so
you may have your antivirus turned on.
Something like that. As I was saying, what it basically means is you're not restricted to the firmware image you've got. Just because you flashed that firmware and just because you're writing an application, you can build different parts of your device at different times and then just pick and choose them the same way you pick and choose NuGet packages to build custom firmware for custom devices to suit whatever your use case might be.
Yes, absolutely. That's relying on interop, and we start with interop from C#, which is basically the same, only that's a lighter version of what you have on the full .NET. And what you do, this usually has a C# wrapper, if you will, and it calls your C or C++ code. For example, if you have a library that is talking to a specific sensor or device that you have for a long time in your company, and that code is completely mad and crazy and no one knows what it does, but you have the C code and it compiles and it does its thing. You can call that from C# just using a wrapper. You put that code that you have on the build system, you compile it along with the rest of the CLR and the firmware, and you can call it from C# using this interop mechanism, and it will just work. As Shoti was saying, when you choose which pieces go into the build, it's with these build options that you see here, and you can pass others from the outside. This is the basic one for the Extensa ESP32 preset. Okay, and you can recognize here a bunch of APIs from the .NET, and with this you can fine-tune what you need, because you may want to do a build for a firmware of your product A, which requires this and that, and you have the same code base for product C that just doesn't need I2C but needs PWM, for example, and you just can pick here which one should be included and not.
So Chris was asking.
Chris is asking what oh, go on.
What I2 speeds work in nanoFramework on an ESP32. I wouldn't have thought the framework actually restricts the speed, does it, Jos?
Say again, I was reading the question.
What I2C speeds work in nanoFramework? Well, I'm thinking, I don't think the framework restricts the speed in any way, does it?
It doesn't, but it could. The thing is that from the IDF, and we are talking about I2C slave, right?
Yes. Well, just I2C in general, I think.
We on the I2C master, when you are instantiating, you can tell on the I2C config parameters if you are going to use the fast or the slow clock speed on the bus. Okay, you can choose that as a parameter. Here on the slave devices, the expressive IDF allows you to select a specific speed for your slave device. The thing that, and this was just for a simplification, it was chosen as a default, so we can save that parameter. Always use the fastest one that's available from the clock there.
I thought it did.
Yeah.
Because I know on all the stuff that I've done, I've always observed my bus running upwards of 400k easily.
Yeah, that going.
Yeah, he's. I think he's just. I think he's just mentioning a point that the RTOS itself has been known to reduce speeds due to interrupt overheads and things like that. So, yeah, I mean, the answer to the question is nanoFramework is not opinionated in that respect. It lets you choose the speed that's appropriate for what you want to do, and it doesn't try to tell you what you should be doing. I mean, if you choose a bad speed and things don't work the way they should, well, that's on your head, you know? But I don't think it'll try and control you in any way.
Yeah, that's correct, because this can be changed. It's just a matter of changing the code that's here. Actually, it's very simple to go here. You can see here, where is this? Clock finds maximum speed here. That's one of the parameters for the I2C config T. Although this is C, you can recognize from the names here on the type. One of these elements of the configuration structure is this maximum speed. When it's put to 0, the IDF, when this is used here, in the configuration on the when you call the param config, it will see, hey, this is 0, so I'm going to the maximum clock speed that's possible. Okay.
Right, so are we ready to move on to the driving motors then?
Oh, yes. Take it away.
Everybody had their fill of I2C? Right. Okay, let me just switch back to my slide deck then. Okay. So, as I mentioned before, when we were looking at the cable and the different wires that are in the cable on an NXT, something I forgot to mention, by the way, just before we move on, if you are cutting NXT cables open, despite the fact that they are quite flexible and bend quite easily, they are ridiculously tough to cut into. So you will need a very sharp knife, and once you get the rubber outer coating off, you need the trick is to get the blade under and slice down the cable so that you can peel the rubber back like that. Then you can clip it with a pair of clippers. And once you get to the wires inside, you will need a pair of proper wire strippers to get to the copper inside the individual wires. Do not try and strip these individual cables using your teeth or your fingernails or anything like that, because I can assure you right now that casing that's on the individual wires is a hell of a lot harder than it looks to be. So, moving on, the motors primarily are driven using just the black and the white pair. And depending on the direction you want to drive the motor is dependent on which one you put the positive voltage on and which one you sync to ground. The signal is a PWM signal, not an analog voltage. If you try to put an analog voltage on it, the motor will just run at full speed no matter how high the voltage is. It's just a question of power rather than speed with an analog voltage on it. So you do need a PWM signal. The duty cycle is where the speed of your motor comes from. And if you try to set them both to positive, I'm not entirely sure what will happen. It's not something that I've tried so far. Actually, I'm jumping ahead of myself a bit there because I do have a comment in the source code relating to that. We'll come back to that in a second. What I have found is that it tends to struggle below 50%. You can use your own arrangement of BJTs, transistors, whatever switching mechanism you want. The voltage needs to be approximately 9 volts. I think the highest voltage I've actually had on any of those wires has been about 9.5, and then the motor just basically refused to work. So there is built-in protection on the system that stops you from overvoltaging things. I believe that's built into the motor itself. That the site that I mentioned before with the information on the crimps and the internals of the NXT cables, there is actually a section on there where the guys cut one of these motors open, and it's quite interesting to look at. So there are various protections built in. However, the easiest way I've found to drive these is just by using something like a simple L293D motor driver, or one of the more up-to-date versions of it, because I think the L293D is actually quite an old part now, and a lot of the suppliers don't carry it anymore. Please do not ignore the big scary red text at the bottom of that slide. If you try and drive this off your MCU, you will fry your board. There is no ifs, no buts, you will kill it. Even if you can deliver the required voltage of a GPIO pin, it's the ampage that these motors draw. The Lego motors draw a little bit more than the normal ampage you would expect many servo motors to drive. The L293D can drive 2 motors at a time, but because of that extra amp draw, you are only going to want to use 1 chip for each motor. I did try to drive 2 motors off the one driver, and it really couldn't supply what was needed. I couldn't get anything less than about 90% on the PWM signal, so before it started struggling, and the chip was getting very, very hot with 2 motors on it as well. Now, you expect these motor driver chips to get a little bit warm, but this was getting to the point where I think it was possibly in danger of softening the DuPont cables that were across the top of it. So the best way to do this is with a separate voltage, which you will connect onto pin 8. And if I just reorientate my camera, you'll see. Let me just bring my camera back. I'll disconnect it from there and run the camera app. Right, you'll see that I've got that separate 9-volt coming in there. That's coming in from just a regular wall wart, and I've got that on its own dedicated 9-volt rail there. Your 9-volt rail ground needs to connect to your MCU ground, and all the grounds on the motor driver chip must be tied together and connected to the same ground. Everything else, the actual power to the motor driver chip itself, obviously the MCU, and all your other bits and pieces of discrete logic, you can take off the 3.3 volt rail on the MCU. So again, yes, on the MCU, sorry. So again, if we move my camera back this way, you can see there's my 3.3 volt rail, and I've got that coming down to this bottom bus bar here, and I've got all the grounds. That's this group here. You need to connect all 4 of the ground points on the motor driver as well. If you leave one of them unconnected, the floating ground will cause the chip not to deliver the 9-volt from the 9-volt rail. And what you'll get in that case is everything will appear to work, you just won't get any output on the motor. For the MCU itself, you need 3 pins. So you need your enable pin, 1 and 2. That's where your PWM signal goes into. And then your input 1 and your input 2 pins, which are driven from those 3 digital pins here. They are the ones that do your actual motor control. Now, if you connect your grounds up properly, and you're doing this sort of with a remote MCU, it is possible to have only the 3 control pins. But because of the way this particular motor driver works, it is much easier just to derive your power off that bus, as I have done. Other different types of motor driver chip may vary. The PWM signals going out to your motor will go from your output 1 and your output 2 lines, and that'll be your black and your white specifically. You don't need a specific separate ground for the actual motor. So if we just sort of zoom in there, you'll see that the NXT motor, none of these other four are connected. I've simply just got the black and the white PWM there going straight across to the motor driver chip. And this is because the motor driver chip will automatically ground the outputs that are switched off. Your circuit should look somewhat like this if you're doing it the same way that I am. So you can see there's your 3.3 system bus, if you like. Your grounds are all tied. Your 9-volt is on its own separate line. Your control lines are on their own separate lines to digital and I/O pins. It goes without saying, keep your 9-volt line away from your other voltage lines. And if you use a heatsink, you also need to make sure that the heatsink's grounded as well. Once you've actually got your circuit put together, the code is, as with anything .NET Nano, ridiculously simple. We start off with just a few constants. So as you can see, pins 4, 5, and 22. So there's 4, there's 5. Those are my 2 input pins, 7 and 2. And then I've got the PWM output onto pin 1. I've set up some statics for my GPIO pins. The GPIO pins are done in exactly the same way as the getting started example you saw earlier on. And the PWM channel just uses the PWM assemblies, nanoFramework.system.devices.pwm, just like the GPIO one. In our main function, the first thing we do is we set up our PWM line. We use a frequency of 40 kilohertz for that. Then we set up our GPIO controller and GPIO pins in exactly the same method as we created the pins previously. Never set both inputs high at the same time. Now, again, as mentioned, I haven't actually tested that, but I can't imagine anything good happening trying to put a positive PWM signal on both lines when one of them's supposed to be the opposite of the other. If you do decide you're brave enough to try it and you observe the results, please do let me know what happened. I'd be curious as to whether things went bang or not. Once we've got our pins set up, then it really is just a matter of setting the duty cycle for the speed that we want and setting the appropriate pin high for the direction that we want to go. So what I have found, and I suspect it's by design, is that if you go lower than a 50% duty cycle, the motor doesn't tend to turn at all. Or if it does try, you can hear it really struggling to turn. Now, particularly with these NXT motors, they are heavily geared inside because they're very, very torquey motors. They're designed for a lot of power and not particularly for speed. Also, at 0.5, that tends to match up with the slowest speed that you can get from the NXT system as a whole. So if you're using the NXTG programming language in the brick, it tends to be about 50% at its slowest and 100% at its fastest. Again, as I've said, you switch the direction of the motor just by setting pin 1 high for forward, pin 2 high for backward. When you're changing the direction, it's probably better to set everything low before you change it. So in this case, if you wanted to switch direction, you wouldn't switch input 2 to high before you changed input 1 to low. But again, that said, This is only on this particular driver chip. It does clearly state in the datasheet, if you set both inputs, it will try and drive both inputs. Other motor driver chips may do it differently. You can change the duty cycle while the motor is running. So if you're going slow and you suddenly want to speed up, yep, you can totally do that. You don't have to switch the motor off. You don't have to stop it or anything between it. You just set a new duty cycle value and away you go. And on that point, I am going to directly just share my camera now, I think. No, I'm not, because I still have the camera application running. So no, I am not. I'm going to go back to sharing my screen because I actually need to load the code, don't I? Right, so we'll go back to that. Sorry, got a bit ham-fisted there. So as you can see, there's the code that we've just sort of gone through in the slides. Less than 100 lines. It really is absolutely nothing. We've included system.device.gpio and system.device.pwm. As with any .NET application, if we go into the NuGet packages, we can see what's been installed, should we need to. And there you go. So in this case, I don't know why I've got the events one. I've possibly put that in without realizing. But in this case, I've got the GPIO and the PWM libraries, again, from the nanoFramework repository. I've provided support specifically for my ESP32. I think that was probably a dependency on one of the others. I can't remember. And as always, you always have the core library. So if I pull this to this side and just shrink that down and shrink that down so that we can see the code. And then I find my camera app again. Where's it gone? There we are. Let's see. Nice. Now I need to just plug this in. Now this will run once because I've already programmed it. So I apologize for the noise. These Lego NXT motors are not well known for being quiet. We'll just let that finish doing its thing. And you can see my COM ports popped up there, ready for me to run this. And I'm going to switch my other camera on now. So we'll just enable that. And yes, has that worked? Let's see if that's worked. Yep, there we go. And we will pop that into there. Now, I assure you, there is a reason for this. I know you're looking at a really weird angle of my desk and my computer monitor there. But if I now run my application so that it comes to its first breakpoint, let's just shrink that down. You can see all the nanoFramework goodness happening there. So let's just step to the first motor part. So there's all the initialization done. That's my GPIO ports. And we're going to drive the motor forward at a duty cycle of 75% for 10 seconds. And as you see, hello everyone. And it's just give it time to wind itself back. And you can see that I've hit the break point for the duty cycle there. Or have I? No, I think I've tripped that up somewhere. Have I? I did. I pressed F5 and it's whizzed through them all. I didn't get a chance to actually step that the way I wanted to. But had I not pressed F5, I'd have been able to step down there. You would have seen that it started it slow, gone up to fast, back down to slow, and then switched the motor off and gone into its infinite timeout at the end there. And as you can see, it's just in its resting state now. We'll get rid of that camera and switch back to the overhead. Nothing to it. It was just a very simple turntable example. Now, what I actually wanted to do, but ran out of time for, I was actually going to put a tilt and pan on this, and I was going to try and set my camera so that I could do kind of a 3D sphere motion. I have one of these things, if you've never seen them, little Bluetooth shutter button. And I've got another one somewhere that I've already cracked open and put a couple of wires on. And with the help of .NET Nano, my eventual project, that this was all the start of, will be to actually have a small turntable which will pan and tilt and turn my phone, and then use the remote Bluetooth shutter button activated via a pin on .NET Nano Framework to actually take photographs to produce a steady sphere automatically. So I'll be able to sit it in the middle of a room, press a button, wait for a delay, walk out, and the Nano Framework will just automate the images that I need to stitch that image together. And that largely is it, folks. So I will hand back to your wonderful host, Mr. Gallagher
there. Love that. I mean, who doesn't love Lego and who doesn't love IoT? So yeah, great. Really appreciated the talk. So thanks very much for that. Thanks to Jose and Pete or Shorty for their contributions to that. It was taken. I know that in the background that's taken quite a lot of effort to get it that talk up and running, and slides pulled together and demos, and all by being ill on Shorty's side as well. So yeah, no, it's that was great. So yeah, I really appreciate that. And yeah, has anybody got any final questions? I mean, feel free to come off mute if you have. And if not, then we'll call it a night.
Yeah, just let me two quick explanations on questions by Shotty. The events NuGet is referenced as a dependency of the GPIO because you have events when you have the pins high and low, and you can listen for that. Right. That's and the runtime, you have to put it there for ESP32 because that the platform calls for configuring the pins, what you are doing with the thing. Hey, GPIO 4, it's an output pin and that stuff. And the other one is PWM, and the other one is A2C. That's the reason why you need that there.
Excellent stuff. Yeah, I figured that there was some kind of dependency.
Yeah, great demo. I would like to see the project that you just described with the pan and tilt camera there.
Well, I'm hoping if people leave me alone and don't ask me to do that strange stuff called work, then I might get some time over Christmas to make it my Christmas project. But
that would be great.
Then again, that said, that wouldn't be fair to the 100 or so other Christmas projects that are still waiting on the list from Christmas's past to be done. So I think this is probably going to become Christmas project 101, maybe.
Love it. All right, folks. I think it's good to the speakers, Jose and Shorty. That was fantastic. Thanks to our sponsors as well, JetBrains and Calix and PJG Creations. Again, we'll be back in the new year with Sander van der Velde talking about our topic. I'm not entirely sure what he's going to talk about yet, but I'm pretty sure anything he talks about will be very interesting as well. Thanks for the comments as well in the chat, and thanks to you folks for coming along and watching. And yeah, do keep an eye out on Meetup for the next one.
Yeah, people are free to hit me up on Twitter and what have you as well. I'm not difficult to find. Just look for Shorty or Shorty_DS or some combination of that.
Yeah, but both Jose and Shorty's contact details are in the Meetup as well, actually, so you can just you can see them in that description section there. So by all means, do. Yeah, all right. And we'll leave it there, and I'll catch you all on the flip side. Cheers, folks. See you later.
Bye-bye, everyone.